Counting our way to probabilities. It's important to know how many events are in a sample space. That sounds easy enough, and in many cases it is. One way to count these outcomes is by listing all of the outcomes out in an orderly way. Sometimes this is too long. This section will introduce counting methods for counting the events in a sample space. A tree diagram uses branches to indicate possible choices at the next stage of outcomes. The fundamental counting principle. For a sequence of n experiments, where the first experience has case of 1 outcomes, and the second case of 2, and the third case of 3, and so forth, the number of possible outcomes for the sequence is case of 1 times case of 2 times case of 3 times however many outcomes there are. Replacement. With replacement, when counting possible outcomes with replacement, objects are placed back into consideration for the following choice. When counting possible outcomes without replacement, objects are not placed back into consideration for the following choice. So like if you're choosing a red from a bag of M&Ms, okay? And your with replacement would be if you pick a M&M out and then you put it back. Without replacement would be you pick an M&M out and you eat it, so it's not there anymore. In order to log into your new email account, you must create a password. The requirements are that the password needs to be 8 characters long, consisting of 5 lowercase letters followed by 3 numbers. If you are allowed to use a character more than once, that is, with replacement, how many different possibilities are there for passwords? So, we need 5 letters. And there's 26 possible letters. So we do 26 times 26 times 26 times 26 times 26. That's 5 times. And then there can be 3 numbers. So that would be 10 times 10 times 10, because there's 10 possible numbers, and I'm not talking about 1 through 10, I'm talking 0 through 9, okay? Multiply all those together, and there are 11,881,376,000 possible outcomes. Let's change the previous example slightly. So you still need a password with 5 lowercase letters and 3 numbers. However, now the characters may not be duplicated in the password, so it's without replacement. So there's 26 numbers that you would initially have access to, but you've already used one, so the second time you only have 25 numbers. Now you've used 2 of the numbers, so there's only 24. Then you've used 3, so there's only 23. And then 22. So that's multiplied 5 times. And then the numbers. First you start with 10 numbers, but after you've already used 1, there's only 9. And after you've used 2, there's only 8. So now there's only 5,683,392,000 possible outcomes. A lot, but less than previously. Factorial. So, if you see a little exclamation mark, that's not meaning, you're happy, you're being yelled at, or anything like that, okay? It means factorial in math. And factorial in math means you start with whatever number it is, and you multiply by each number lower than that. So if you say have 5 factorial, then you'll do 5 times 4 times 3 times 2 times 1. And then something that you need to note is that 0 factorial isn't 0, it's 1. Calculate the following factorial expressions. So 8 would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 40,320. 3 factorial over 0 factorial would be 3 times 2 times 1 on the top and 1 on the bottom. So that's 6 divided by 1, or 6. 89 factorial over 87 factorial. Oh my goodness. Don't think you have to write all these out. Let me show you a little trick. If we start with the top, 89 times 88 times 87, I'm going to stop there. Going on down from 87 would be 87 factorial. Notice on the bottom we have 87 factorial. Those can now cancel out. So all we're doing is 89 times 88. Oh, and that's it. Just 89 times 88, which is 7,832. So that's a good little hint there, is instead of writing it all the way down, look and see if there's something that you can cancel out. 7 factorial over 5 minus 1 factorial. Notice the 5 minus 1 is in parentheses, so we go ahead and subtract here to get 4 factorial. And so we can say 7 times 6 times 5 times, I'm going to stop with 4. Since we have 4 factorial on the bottom, I can cancel those out. And so all we have is 7 times 6 times 5. That is 210. And the last one, 5 factorial over 3 factorial times 4 minus 2 factorial. So we're gonna go ahead and reduce in the parentheses there, so we know what we can cancel out and all. 4 minus 2 is 2, so that'll be 3 factorial times 2 factorial. So I'm just going to start, and I'm going to make sure that we could either cancel out the 3 factorials or the 2s. Better to cancel out the higher one. So 5 times 4 times 3 factorial. And on the bottom, we still have 3 factorial times 2 factorial. The 3 factorials will go away. So we have 5 times 4 on the top and 2 times 1 on the bottom. That's 20 over 2, or 10. A combination. Combinations involve choosing a specific number of objects from a particular group of objects, using each only once, when the order in which they are chosen is not important. So the big thing to remember here is order not important, because that's going to be the difference between a combination and a permutation. Permutation involves choosing a specific number of objects from a particular group of objects, using each only once, in which the order they are choosing is important. So again, for permutation, the order is important. For a combination, it is not. So before you work a problem, you'll need to ask yourself, is this a combination or a permutation? The number of ways to sell R objects from a total of N objects is found by the following 2 formulas. When order is not important, you use a combination. NCR. What does that mean? Well, a total of N objects and you're wanting to select R. So that would be your total factorial over the number you want to select factorial times the total minus the number you want to select factorial. And then a permutation is when order is important. NPR is N factorial over just N minus R factorial. Notice the only difference is in combinations we have this R factorial also on the bottom. Let's calculate the number of possibilities for our sandwich. Suppose there are 18 toppings to choose from once you've decided on bread, meat, and cheese. How many possible sandwiches are there if you choose 4 different toppings? So, there's 18 possible and you want to choose 4. So remember, we're using, this time the order is not important, so we're using a combination. So N is 18, R is 4. Okay, so let's see. On the bottom, we'll have 4 factorial times 14 factorial. So on the top, we'll do down to 14. 18 times 17 times 16 times 15 times 14 factorial. So our 14 factorials will go away. And so we'll just need 18 times 17 times 16 times 15 on the top, and 4 times 3 times 2 times 1 on the bottom. There are 3,060 different sandwich possibilities. Consider a race with 140 participants. How many possible outcomes are there for the top 3 positions of gold, silver, and bronze? Now, this time, gold, silver, and bronze, there's an order there. So order matters. We have to use a permutation. There's 140 total participants, but you only want 3 of them. And this is your formula for permutation. So 140 factorial over 140 minus 3 factorial. We end up with 137 factorial on the bottom. And I'm stopping at 137 because I know that they will cancel out. And so we just have 140 times 139 times 138. That's a big number. 2,685,480 possible ways the top 3 spots could be awarded. How many possible ways are there to arrange the order of appearance for the contestants in the local talent show if there are 15 contestants altogether. And again, in this one, order does matter. We want an order of appearance. So we're going to use a permutation. There's 15 possible contestants and 15 possible people to order, I guess. It's hard to say. So that would be 15 factorial over 15 minus 15 factorial. So on the top, you've got 15 times 14 times 13 times all the way to times 1. And on the bottom, you just have 0 factorial, which is 1. You can put in your calculator 15 times 14 times 13 and go ahead and do that. And you get that there are 1,307,674,368,000 possible choices. In a graphing calculator, I know that there's a factorial button. If you go to math, the math button, one of the first ones on there is the little exclamation point. So you can put in 15 and then go to math and select that exclamation point. On a scientific calculator, I'm not really sure where to tell you because they're all different, where to tell you to find that. Permutations with repeated objects. The number of distinguishable permutations of n objects, of which k sub 1 are alike, k sub 2 are alike, and so forth, is given by this. N factorial over k sub 1 factorial times k sub 2 factorial times k sub 3 factorial times so on. To help you understand what this means, we'll look at an example. How many different ways can you arrange the letters in the word Mississippi? So we first need to talk about the number of letters. N will be the number of letters. There's 11 of them. And then your K's would be how many of each type letter there are. Okay? So K sub 1 would be M, and there's just one of those. K sub 2 would be I. There's 4 I's. K sub 3 would be S. There's 4 S's. And K sub 4 would be P, of which there's 2 of. So when you fill in your formula, we're only needing k sub 1 factorial times k sub 2 factorial. We're only needing it 3 times on the bottom with n factorial on the top. So we'll have 11 factorial over 1 factorial times 4 factorial times 4 factorial times 2 factorial. I'll take this to the next page. So let's see. 1 factorial can just go away. We don't need that. It's just 1. And if we start our 11, I forgot my factorial there. And the largest number on the bottom we've got is 4. So we'll go down to 4. 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial. So those 4 factorials will go away. So we're still left on the top with 11 times 10 times 9 times 8 times 7 times 6 times 5. And on the bottom we have 4 factorial, which is 4 times 3 times 2 times 1, times 2 factorial, which is 2 times 1. Put that all in your calculator and make sure that you put the top in parentheses and the bottom in parentheses. If you're putting it in your calculator, you get 34,650 possible ways to arrange these letters.